Okay, good morning. Thank you very much for attending this session on the graduate certificate in the Internet of Things, which is short code GCIOT. So my name's Conor McCardle, and I'm the program chair of this program, and it's provided by the School of Electronic Engineering in DCU. So this session is to give you some additional information about the program and to answer any questions you may have about its content, where we see the program fitting into the industrial landscape, where the skills will be used, and how to apply and so on. So I'm also joined by Professor Anne Morrissey, who oversees all of the Springboard programs in the faculty, and will be able to take questions at the end as well, if you have technical questions about the application process and so on. So just a couple of housekeeping things for the session. So your mic and camera should already be muted, I believe. So this session is being recorded. So if you have any questions that occur to you during the session, you can post them in the Zoom chat or in the Q&A window. So you'll find those controls then at the bottom of your Zoom screen, and we'll get to those questions then at the end of the session. So I'll also share these slides of some live links to additional information. So we will share a PDF of the slides for your reference after the session. The recording will also be available. Okay, so before I introduce the program proper, I just want to say a little bit about, to introduce Dublin City University, just in case you're not already familiar with us, and also about the School of Electronic Engineering that provides this program. So Dublin City University is consistently a highly ranked university. So there's a number of metrics that are used globally to measure university performance, and we perform very well in these. We're ranked in the top 2% of universities worldwide. A particularly important metric for us is that we're ranked 19th in the world for graduate employment. So that's across all universities. So in common with that goal in the School of Electronic Engineering and for this program, it's very much targeted, and all of our programs are very much targeted at real world skills and employability and career development. So we are a relatively young university, which means we're less than 50 years old. We're getting on for 45 years old, I think, next year. And we're currently the highest ranked young Irish university, by that definition, being less than being 50 years old or younger. And we're also proud that this year we were voted the Sunday Times University of the Year as well. So generally a strong university to study at. So a little bit about the School of Electronic Engineering then, and our taught programs. So we've been running level 9 or master's programs for a long time. We started our master's program back in the early 90s, and it's the longest running MEng program of its type in the country. It's always been driven by innovation in how we teach and deliver modules. So specifically, since 1997, we've offered a flexible remote or online option for taking the modules in the program, or a mixed mode where you attend some lectures on campus and some online. And this was driven by a demand in industry to allow part-time students working in industry to upskill through our more advanced programs at level 9, master's programs and graduate certificates, and so on. So I think it's important to mention this, particularly in the context of this COVID era that we're now experiencing in online teaching, that we've been delivering programs online for many years. We've a lot of experience in that, and this program is no exception. So we can deliver programs online in a very high high quality manner, and our online offerings aren't just a recent reaction to moving online due to COVID. So the programs that we offer at undergraduate and particularly master's level are continually renewed and updated. So the topics covered are very much the cutting edge of technology. So it's very important that we keep in touch with the latest in research, and also the latest demands from industry in terms of skill sets that are required for industry now and into the future. By doing this, we've found that we've always had a very high employability rate from our programs, and the programs are very targeted at the needs of industry, not just to cover the particular technologies that industry see as important over the coming number of years, but also to give you the important foundations in technology that last for a career, right? That are the foundations for all, or for most future innovations in technology that we can envisage. So that's an important mix, having the solid foundations and also state-of-the-art knowledge that's industry ready straight away. So just to say further to that in terms of what informs our teaching, so all of our teaching is very much research led, and all of the staff are what we call research active. That means that they participate in research, either involved with university research centres, such as Entwine, which is a networks research centre, or national research centres, such as Insight, Adapt, which relates to materials processing, or Connect, which relates to networks. So many of the teaching staff are founding members of national research centres and programs, and heavily involved in research, which keeps a very strong connection with not just other universities, but with industry. So, so pretty much all research these days must have some direct connection with industry and to serve societal needs. So it's very much driven by what government sees as important for the economy of the future, at the present and the future. So this experience is key to keeping our programs continually updated and relevant. So I'll just move on more specifically to this particular program, which relates to the Internet of Things. And just in case you're not entirely familiar with the Internet of Things, because it's a term that's bandied about quite a bit and means different things to different people, I just want to give an overview of what we mean by the Internet of Things, and from that, then what specific topics are covered by this course. So generally, the Internet of Things relates to the engineering of computer devices. So we're very familiar with modern computer devices, from smartphones, laptops, tablets, PCs, and we'll be familiar with data centers and cloud and terms like that. So this is kind of the familiar world of computing, but in parallel with that world that we're familiar with, there is also, if you like, an underlying world of small embedded computer devices that are in all sorts of devices and technologies these days, and that's what this course mainly focuses on. So the Internet of Things centers generally around the concept of something called a microcontroller. So a microcontroller is a small single chip, self-contained computing system that has network connectivity and is very low power, and typically is a very cheap device in the order of cents. in order of cents when these things are bought at industry scales and embedded into systems. So the types of things you'll find microcontrollers in are, for example, the modern car will have several hundred microcontrollers, where each microcontroller is dedicated towards doing some specific function. For example, it might sense the tire pressure in an individual tire and signal back changes in tire pressure. They are embedded into the engine management systems. In electric vehicles, becoming more and more important to manage the usage of electrical batteries and how the car is running for efficiency and so on. So these devices are embedded into everything. We can now buy light bulbs that have microcontrollers incorporated so that we can turn on and off lights remotely or have them turn off by themselves if there's nobody in a room and so on. So this whole world of microcontrollers and embedded systems is actually much larger than we might think, because it is kind of under the surface. So to give an indication, in terms of microprocessor sales, last year there were about 2 billion sold, and most of those ended up in smartphones and tablets. Whereas the sales for microcontrollers, these tiny embedded computers, was closer to about 10 times that volume. So these are really proliferating in terms of their use in all sorts of applications. Coupled with that as well, the amount of data that microcontrollers produce. So typically a microcontroller is connected to sensors. Sensors generate data, and microcontrollers need to do something with that data to implement a useful application. The amount of data generated, raw data generated by IoT sensors or microcontrollers is about 5 times the volume that is flowing around data centers. So that the data in data centers is where most commercial or consumer data that we're familiar with exists in data centers, but IoT devices are generating a huge amount of additional data as well. So the importance of that in terms of data, and then how this fact relates to an integration of software systems and microcontrollers and electronics in this course, is that, of course, this raw data from IoT sensors can't be directly shipped to the cloud for processing to do something useful in an application, to control something. It needs to be pre-processed locally. So you need intelligence down at the microcontroller and sensor level to do data analytics with data, rather than shipping all raw data to the cloud and so on. So this introduces then the need to have expertise in devices, networking, data analytics, software topics, and so on. So when I say the Internet of Things, I mean all of those topics being encompassed in order to realize end-to-end, useful end-to-end applications. So more and more, the Internet of Things becoming important in targeting solutions for global challenges. So water scarcities, food production, control of energy, and so on, remote health. So all of these applications rely on being able to remotely sense data. For example, checking the soil moisture contents in fields, for example, is critical. So that's a typical IoT application. Sensing the quality of water, microbial contents, and so on. Again, extremely important for managing what is becoming a scarce resource, water, and managing, for example, feeding wind power into the grid and other renewables into the grid. You need sensor data to be able to predict what energy you can get from a farm, and so on. So the area is transitioning quite quickly to what we're maybe focused home device management applications, car sensing, traffic management applications, process control in industry, but now also becoming very important to solve these impending global challenges that we have in these areas. So there's an accelerating demand in industry for IoT engineers at the end of the day. There is very high employability. There's a shortage of engineers in this area. So more specifically then on how that definition of IoT relates to the program coverage that we have on this program, GCIoT, you will take 5 key modules that are selected from our master's program, so the same modules that appear in the master's program. You have 4 level 9 advanced modules plus 1, there are the 5 XX modules shown here on the right, plus 1 level 8 module that supports those, plus an additional technology and ICT career success module, which is particularly useful for this program if you are planning on transitioning your career from maybe a different path to something more focused on these modern technologies. That's a very useful module to support your career transition. So it's a soft skills module. So the coverage of the program is really end-to-end in terms of what I've just described. So all the way from the sensor, processing of low-level signals, all the way up through networks, software, operating systems to cloud systems, where data is stored, managed, or where decisions are made and control decisions sent back down to devices. So that covers from advanced engineering fundamentals and devices, the mathematics of signal processing and so on, to state-of-the-art technologies, so the types of network protocols that are being introduced to support IoT, which are specialized for low-power devices and long-distance communication, and engineering design skills. So there is, as well as covering fundamentals that will have very good longevity in a career, there's a lot of practical assignments and projects in the modules to support your practical skills and very transferable skills to industry. So I can categorize them broadly as software, so software languages, Java, C, C++, Python, real-time OSs, Linux operating systems, and software towards embedded system software, so drivers for sensors and so on, hardware and interfacing. So it's as an engineering degree, we are not afraid of getting down into the hardware, into the mathematics of signal processing. And this, and this gives this course an edge over purely software-driven or software-focused course for IoT. So we also cover real-time digital signal processing and hardware that supports that type of processing, so field programmable gate arrays, specialized configurable hardware for processing signals at a low level, and interfacing protocols with sensors and so on. And then to connect hardware to the cloud, of course, we need networks, and we need to cover a particular type of, or a very broad type of network, very broad selection of network specialties in IoT, because we're interfacing low power sensors, so we need low power long distance communication protocols like 6LoWPAN and so on, but also locally maybe Wi-Fi and so on. But we also need to understand the network infrastructure in the cloud, so TCP/IP. So there's a broad coverage of networks. And then lastly, data analytics. So there is a module on data analytics and machine learning, which is key to interpret and filter very large amounts of data from sensors that need sophisticated mathematical and data analytics techniques in order to get value out of the and to interpret the sensor data. So these are the 6 modules on the program. They're all 7.5 credit modules. There's a detailed module descriptor at this link, which gives you a breakdown of the topics covered and the types of assessments and so on. So I'll just outline briefly the kind of shape of the program then and the schedule of modules. So the 6 modules are distributed like this between 2 semesters. So semester 1 starts in September, the end of September, and runs till the end of November. And in semester 1, you would take 3 modules, E42, 5.4, and 5.15. And then in semester 2, you take 3 modules. So I should mention the technology and ICT career success module is actually spans both semesters 1 and 2, but most of the CA deliverables are in semester 2. So there is still a reasonable balance there in terms of workload across the whole year. So exams are before Christmas. There's a break before you head back into semester 2 on the 10th of January. And again, there are exams for the semester 2 modules in April. There is an opportunity to resit CA or exams if needs be in August. So just in terms of time commitment then, which is important to know, particularly as this is a part-time course and most or many students will be working full-time or part-time whilst taking this course. So the nominal contact hours for one of these modules is 190 hours total. So that includes lectures, working on assignments, study and exam prep. So that's in total. So if you add up across 3 modules in a semester, that number of hours, that would nominally come to 40 hours a week. I should say that that's a nominal number and it is high. For students coming from an engineering or computer science or cognitive discipline into this course, you would not be expecting to start learning all of the topics from scratch. You'll be familiar with the introductory parts of these modules. So you would be expecting that you would be more looking at something like 25 hours a week in that case. So 40 hours per week would be at the very high end if you hadn't any experience in any of these modules previously. So it's only a nominal number. But nonetheless, it is important to point out that it is a commitment in terms of time. It's a level 9 engineering program. So you expect a commensurate workload for that reason. So just to mention the dates that are shown here for the semester they should stay the same, but at the moment I believe they're still provisional. So there's a link here where you can check the current dates published in the DCU academic. So just a little bit then about online delivery of the program and the supports that we have in place. So DCU, as per the government's drive to get 3rd level education back on campus in September, DCU will be back on campus teaching in September. However, as I've mentioned, all of our postgraduate taught programs and modules we've always delivered as an online option. So that is certainly that option is certainly available for all of these modules if you want to study entirely remotely. As we will have at least some activities for these modules on campus, you could also choose to mix some on campus study with remote as well. So there would be that option. But regardless, all of the online supports are in place for online delivery. So we deliver lectures by Zoom or similar systems, and then have screencast recordings. We will generally also supplement that by live Zoom tutorials or questions and answers sessions for each module as well. We have an online virtual learning environment called Loop. This is essentially a version of Moodle, which you might already be familiar with. So all materials are well organized there for each module. Materials are introduced typically on a week-by-week basis, so you're not flooded with material at the start of the semester. And there'll be constant contact from lecturers in terms of material that's been posted, to give you signposts as to where you should be during the semester. All modules also have a continuous assessment, which is introduced during the semester. Modules are supported directly by module coordinators. That's the lecturers, the professors, rather than teaching assistants or anything like that. So you have a direct line of communication with the lecturer for all modules, and they keep in frequent contact with students, can answer queries by email, and typically also have online sessions for the class as well. There's remote access to DCU library, the DCU library. Most of the, pretty much all of the supporting academic papers and books in our area in engineering and computing are available online in the DCU library. You can access, full access to those. And in terms of any software or hardware that you need for the course, we aim to keep all software open source. So all you need is a laptop. It doesn't need to be particularly high spec or anything like that. So you can download software for the modules. If there is any specialized hardware, we will send that out to students. And we have done this, over the previous years with online courses, and it works. That works well. In terms of attendance on campuses, I've given a link here to up-to-date information on attending campus, attending DCU campus next academic year. So you can keep up to date with any news at that link. So just to mention that the graduate certificate in the Internet of Things has been specifically designed so that it's very easy once you've completed it to transition onto the Master's in Electronic and Computer Engineering program, if you wish. If you want to do that, you'll already have taken 5 of the engineering taught modules, and the requirements then to complete the MEng would be to complete a further 3 taught modules plus a master's project. So all of the engineering modules you take on GCIOT are selected from the master's program, so they all would directly transfer to the master's program. So this is an option that's been quite popular with our GCIOT students in the past. I think we have 5 transferring into next year onto the master's, having completed GCIOT last year. Just to mention that GCIOT is a Springboard funded course. If you transfer to the master's, then that is not supported by Springboard. That's a new program. You would have fees, but you'll already have covered a large portion of the credits for the MEng. So it would be significant overall reduction in the fees for the MEng if you go this route. So I'll just say briefly what the MEng would entail if you were to transfer to the MEng. So we organize the MEng in terms of majors options. So a major entails taking 4 specialized modules plus another 4 modules plus a project. So the major in the Internet of Things on the master's aligns very well with the graduate certificate. If you take the graduate certificate, you'll already have taken 4 the 4 core modules for the master's major, plus one of the optional modules, and you just do 3 additional taught modules on the project to complete. The modules on GCIOT also quite well align with the image processing and analysis major, so that would be another option that you could consider if you wanted to go on to the master's. So just very briefly outlined what they look like in the master's. So this is the MEng in the Internet of Things. So the 5 green modules there are on GCIOT, so they would be completed. And we'd recommend 3 specific modules we'd recommend as additional complementary modules then to complete your set of 8 modules in the masters. But there's a broad selection. There's a total of 38 taught modules available on the level 9 electronic engineering programs. It's a broad choice, so you can really specialize your program as you wish. On the image processing major, on the MEng, if you were to transfer to this after GCIOT, you could transfer 4 of the 5 engineering modules, and there would be 2 additional specialized core modules, E507, E544, if you were to take this major. So that would also be a possibility as well. So finally, then on some details on how to apply. So you apply through Springboard. So this is the link for this specific program, and the course code for GCIOT is TC839. So the deadline is August 1st, which I believe is this very week. So there is time to still apply. So if you're interested in applying, please check out this link to see what documents you need to provide, so you have time to put those together. If you've just completed an undergraduate course and you don't yet have full transcripts, you can still make your application, and we can make a conditional offer. It's possible to make a conditional offer, and you can provide your transcripts later. So the entry requirements then are an NFQ level 8. So that's typically a 4-year honours degree in electrical engineering or electronic engineering, or a related engineering discipline such as mechatronic engineering, or applied physics that had some computing and some electronics, or a computer science degree. So the key kind of prerequisites are that you've covered engineering maths or some equivalent mathematics, that you have some experience in software. So any discipline that would provide that would align with the requirements. If you don't have a level 8, then we can also consider applicants with a level 7 in a similar topic, plus 3 years minimum relevant experience in industry. So just to say that all applicants may be subject to interview. So the fees then, if you are in employment, or if you have just finished the program, and Anne might be able to correct me if I'm wrong on that or give further information, but if you're in that category, then the fee for the whole course is just 405 euros. So that is approximately only 10% of what the normal fee would be. If you're currently unemployed when you apply, then there is no fee at all. And some contacts. So if you have administrative queries, you can send them to Anya Nolan. And if you have any queries about the details of the course, the academic content and so on, I'm happy to answer any of those queries. So you can contact me directly.